Vamos. Okay, welcome everyone to this seminar shared by Lacan and Sidney. Today we have Diego Garbervetsky. He's a professor at University of Buenos Aires and the the Argentinian Research Council. He's also the director of the Institute of Computer Sciences in Buenos Aires. He works in software engineering, so it's not the usual talk. That's the typical talk that we have here. So he's going to talk about software engineering, and in particular, his research is related with analysis of programs, semantic and symbolic analysis of programs. So Diego.
Thank you, Sergio. Thank you, everyone, for coming here. Okay, as I mentioned, I'm Diego. I am visiting Sergio Slotnick with Virginia, that is also here. We are trying to help Sergio to verify some guidelines that implemented with some students. So, as Sergio mentioned, maybe my topic is a little bit different, but I will try to make you understand. If not, we can discuss offline and go into details. So, just to give you an idea of what are my research interests and what I work usually, I try to develop program analysis techniques. When I say program analysis, you have to think about code. Program, piece of code, that's a piece of text. I try to get information out of the code, for instance, to somehow infer properties of the code, for instance, memory consumption, or maybe you have a big piece of code that you have in GitHub or something, you want to understand the architecture. So the idea is, given the code, to automatically infer something, properties. Something that I'm also very interested is about verification and testing, automatic testing of code. This is why I'm trying to help Sergio here. And then I also have application, of course, that I'm interested in. The first one is quality assurance, to make the quality of the code better. Validation is another task, is when you have a code and then you have an idea, try to see if the code somehow implements your idea. It's more like a mental thing, it's more informal. Understanding, but it's also informal. The idea is giving the code, maybe I can infer something that can help you understand better the code. Of course, the typical things that people that work with code does is to perform some code optimization, like a compiler, that maybe you work with compilers. Transformation, to translate from one language to another language automatically. And of course, one thing that is very appealing and important now is security. And this talk is more about security, but with a combination of things. So now, okay, this is the title of the talk. It's quite large, sorry. So the idea of this talk is a word that came from a collaboration between Microsoft Research, GitHub, that actually GitHub now is part of Microsoft, but you can distinguish what Microsoft does and what GitHub does. And I was like a virtual visiting researcher during the COVID. I worked for about 9 months with them, and this is Anita that helped us to do that. And the title is very long. It's something like leveraging code similarity and using feedback for effective time specification inference for JavaScript. I don't know what the title is so complex I cannot explain, but I will try to tell you why the title is so long and all the things that we did. So, what is the purpose of this work? We are concerned about security vulnerabilities, in particular in web applications. So, I guess even if you don't, maybe you are not in my field, you use the web a lot. And you use Gmail or you use another kind of tools online, and you always have to maybe introduce some sensitive data, like your password, or maybe you want to do a transfer to someone. So this is very critical, and unfortunately there are still a lot of issues with this kind of application. They have a lot of vulnerabilities. Just to mention a few, one that is very typical, one is SQL injection or NoSQL injection, which is essentially you somehow, given a web page, you introduce some data that indirectly affects a database. So maybe you are very clever and you insert maybe in the header of the web page, or maybe in a field when you insert some data, for instance, your password or the destination of a transfer, you put some data in a clever way that you end up affecting the database. And that affects, of course, maybe other person, or maybe you delete the whole database and the application stops working. There is another kind of thing that is similar, but the idea is instead of doing something with the database, you somehow, you are super clever and bad person, and you insert some code. So you make some special characters and you insert some code, that some code end up in the final application. So another user, then when they come again to Gmail, that code is executed with his database of his data. So this is very dangerous. This is cross-splitting, and it's maybe the most dangerous kind of vulnerabilities. And another example is you typically, I don't know, maybe you work with Linux or Windows or Mac, you have to access your disk and you have to write paths. There are some vulnerabilities that allows you to access some path that is forbidden, for instance, the root path or someone user path. So there are some kind of vulnerability that we are worried about that, and we try to avoid that. So there is like a technique that is the master of the techniques to try to mitigate that kind of vulnerabilities, and the name is taint analysis. Have you heard about this taint analysis? Okay, let me explain very briefly in the next slide. My idea is to find somehow some flow. What is a flow? Is you have a program that has several instructions. Maybe there is a way there is one instruction that receives some data, for instance, your password, and there is some another instruction that prints some data. If the instruction that prints data prints your password, it's not okay, because someone is going to see the password in your screen. So the idea is to find some flow from some sensitive data to an output. The idea is if you find that, there is a vulnerability. This is the main idea, but I try to explain in this example. So these green points are program points, statements in your code. Maybe C code, maybe I see that you can write code. So there are a lot of statements, and the idea is if you can find this vulnerability, so there is something that, there is a metaphor that we call source. A source is essentially a place when you insert sensitive data. For instance, a password. Okay? And there is something that we call sink, is when you somehow open this data. It can be you log something, you put something in the street, you write it in a database, whatever. So if you find some way to go from the source to the sink, it's not good at all. So this is a vulnerability. There are cases where you have some sensitive data that moves in your code and end up in some place, and nobody sees, and that's good, because it's not vulnerable. And another thing that can happen is that, okay, you have your data, and before going to a sink, before being shown, it is sanitized. For instance, your password is encrypted before being stored in a database. So this is okay, because you protect the data. So I think analysis try to discover these things. In particular, try to discover paths from a source to a sink without passing through a sanitizer. That's a vulnerability.
Sorry,
yes.
You mean optimize?
It doesn't optimize. It just look. It's like if you take the code and they say, okay, I found a source because there is a. I see that I recognize in the code that someone is asking for a password. In the code, in C code or whatever, or Java, I say get password. This is a source, and maybe 20 statements later, you see that there is print password. This is a vulnerability. If you can show that from that statement to that statement there is a path, so you can execute that, and you start from that and end up in that print, this is vulnerable. It can happen that in your code, you ask for a password, and after asking for a password, you just exit your program. So the other statement is not reachable, actually, because it's in the code, but it's not reachable. Or maybe it's protected by an if statement or whatever. So this kind of analysis, what it tries to do is to say, okay, if there is a potential path from this point to this another point, when I mention point, you have to think about code. This statement and this statement. Okay.
And sorry, I mean, all of these are synced. I mean, all the end because you put two T.
No, the
green tick and
so the idea is all the green points are statements in the code. Line 1, line 2, line 3, 4, whatever. And then you recognize some points as source and sink. Why? Because you know, for instance, you say something that says get password. Okay, this is a source. And in your code, you say something like log this variable log, write a log or write in a database or print, the statement print in screen. So you mark this as a sink. And then there are many other statements that are not sources, they are not sink. For instance, you have in your code something that says x equal x plus 1 is not even. It's not a source, it's not a sink, it's not a sanitizer, it's just code. So from your code has a million of statements. Some of them are sources because they read, they get sensitive data. And they are sinks because they print or save sensitive data. And they are sanitizers because they just transfer the data to make it more secure. This is the idea.
And the analogy of the source is input and the sink is output.
Yes, there are another kind of source and sink, but this is the basic idea.
Okay.
If you think about input is a source, and output is a sink.
Okay.
Okay? So the idea is that someone came with this idea of this technique of taint-tracking, and with this technique you can really check for these vulnerabilities. So the problem is, as you may see, and here Garbervetsky, is that how do you know that something is a source, something is a sink, something is a sanitizer? Okay, this is an issue. This kind of analysis relies on knowing which element is a source, which element is a sink, and which element is a sanitizer. And in general, this is not so easy. Maybe you know it in your own code because it's small or you have a lot of knowledge, but in general, it's not so easy. And in reality, when you write code, even in C++, but in general, when you write using a framework or libraries, what happens is that you have some piece of code, which you call a client, which relies on a lot of libraries. I know if someone has to write something in Python or C++ and use some library for instance, to do some graphics or plot something, you don't write that code, you use that code. So this is a library. So the problem when you have that is maybe the sources and the sinks are in the libraries. But you don't know the library, you just use the library. You don't know how it's implemented this function plot or a particular function, I don't know, in C++. So this is an issue. So in general, yes.
Two questions. One is, do you assume you have access to the source code or to the compiler code? That's a little bit.
So this is my next slide. What happens in reality is that you have access to your code. Maybe you have partial access to some library, but in general, you don't have access to the libraries that another colleague implemented. Maybe you know the name of the functions, but then you don't know the code. And this is what happens. So you don't know where are the sources and the sinks and the sanitizers.
The other question is, you were talking about sensitive data.
Yes.
So there is a category of data which is sensitive, a category of data which is not sensitive. So
yes.
That's also something that you have to know before doing this analysis.
Yes, and if you have your own code, you know that. But when you start to use libraries, they are. Exactly. No, this is terrible. It's not good. But we try to challenging. We didn't solve it, but we try to come back to mitigate a little bit. But this,
I understand that the main goal is that you want to get a piece of code without knowing anything and being able to categorize where are the sinks, where are the sources in an automatic way.
Yes.
That's the final goal.
Yes. The actual goal is to try to execute a security query, but the security query requires knowing this element. Yes. So the problem is more difficult because actually your code now maybe is super small, like 10 lines of code, but uses a lot of libraries. Especially when you write web applications which are super complex. Actually, the code that you write is very small. It's interaction with libraries. So it's difficult. So let me give you an example. You don't have to understand the code. I don't even care about the code. Just to show you one example of what are the elements. This is a typical code written in JavaScript. It doesn't matter if you don't understand because it's not relevant, really. What is relevant is that it has two parameters. One is the red one is the user request, is the input that came from the browser somehow. So you execute something, you press a click in your browser, and some data come to to that function with data from the web. And the other one, the green one, is the response. Maybe you compute something and then you return that to the browser, okay? And in this case, what we are going to do is to process the input that came from the browser. So in this case, we take the input, this particular term, we extract something from the body, doesn't care, and we somehow pass this data through a function. And at the end, this is a function that processes the data, just transforms some text, replacing some things. And at the end, we use this data that we process to find some record in a database and replace with some information. So this program takes an input that came from the browser, maybe sensitive, process it someone, and save it in a database. And open. So we can recognize that we have a source, we have a sink, because this is a source because it came somehow, it's related with the input. We have a sink because it's accessing a database. And we have, in this particular case, so we have a flow from source to sink, but we are safe because there is this function that this well implemented is a sanitizer. So we have some input is processing and transform it with the sanitizer, and at the end it goes to the sink. So this is the kind of things that we process with a taint analysis. Doesn't matter if you understand the code, I don't care, because it's not important, okay? But this is the three elements in an actual program.
So by sanitizer, you mean a function that it makes a relation between the source and sink?
Yes, the sanitizer is a function that transforms the input that is sensitive in something that is secure somehow. In this case, it doesn't matter well, but if you take an input from the browser, and if you don't transform it, especially if you don't remove some escape characters, you are in danger of having a vulnerability like NoSQL injection or cross-site script, because you can put an escape character and then put some command. So in this case, you replace those escape characters and they don't have some effect. So you are sure, you are more secure. This is the idea of sanitizer. Yes, so there is a function that takes the input and produces an output, which tries to sanitize it, to make it safe. Okay? Okay, I continue. So in this case, a tool for instance, that is a taint analyzer will say that it's safe. Okay, the problem is how we infer automatically such taint specification, which Sergio already mentioned. So to give you a little bit of the context, we were working with GitHub. GitHub has a very good taint analyzer, very powerful. The name is GraphQL, and they can produce security queries, for instance, for taint analysis, etc., site scripting, NoSQL injection. And they already, because they have a lot of employees, they have these queries, and they have a lot of source and things and details already modeled for many levels. So they have a lot of things well implemented. So they take this specification, they propose, they give this service to the client that you have a repo in GitHub, you have your code in GitHub. They run the analysis for you for free if you are a student or something, or paying if you are a company, and they give you security alerts. Okay, so this is super cool. The problem is that if you have incomplete taint specifications, you are missing alerts. And this is always going to happen because there is all the time there are new levels or updates to all levels. So it's impossible to catch up with this manually modeled specs. So this is a problem that this has. So, of course, you already know this is challenging because there are a lot of libraries. If one possibility is trying to infer this specification automatically by looking at the code of the library. But the problem is that JavaScript is a very difficult language. I don't know if you understand what the meaning of dynamic, but for instance, C and C++ are languages that they are difficult, but are okay. Maybe when you write something, you compile it and you run it, and somehow it's the same, what you run is the same that you compile. In JavaScript it's different. You can generate code on the fly and run it. So you can write one code that output codes, and that code executes. So it's very difficult. Manual inference, as GitHub does right now, is difficult and it's error-prone. And we have this problem that have to be precise in order to provide good alerts. So now our approach with all this introduction. So what we propose is, okay, we propose an approach which is somehow a combination of pro-analysis, is what I do, with machine learning. Why pro-analysis? Because we are analyzing code. Of course, we have to apply some technical pro-analysis, like tainting. Why machine learning? Because GitHub has a lot of repos, a lot of code. And when you have a lot of code, you find similarity between codes and you can learn something from that. So the idea is to use these two powers, the power of analysis and machine learning, to infer automatically these specifications. Okay? So the basic idea is you start with maybe some basic specification, the one that GitHub already has, that's all queries with some manual modeling, and a lot of training projects. You apply our tool, and then you run our tool with some test project, and then with feedback of experts, that I will show you that later, you can produce this specification. In particular, we care about things, because things are more difficult to find than sources and sanitizers. Okay, to give you an overview of the approach, you stop me when you think that it's too much. We have several phases. The first phase is the most, for me, is the most interesting for you. I will try to explain more about that, and the other parts are more machine learning, typical machine learning stuff. So the first part is the one that applies pro-analysis and a little bit of machine learning, but in a different way, using linear optimization that takes a lot of codes. It somehow tries to learn the roles of different pieces of code. For instance, if something is a source or appears to be a source in many codes, it's likely to be a source. This is the idea, or a sink, or whatever. So the idea is of this first stage is to try to predict source in sanitizers using somehow a probabilistic approach by reading the code. The second one is a refining phase. Okay, I produced some specification. We knew that it's not very precise, maybe produce too many specifications. We refine it using a technique based on Similarity. I will explain that later. And finally, we have a phase when we show you the result on the screen, and experts say, okay, this is good, this is bad, this is good, classification, manual classification. We call triaging. So, with all the results, the idea is to produce new specifications that GitHub can use it to produce. So, given all specifications with our approach, we generate new specifications that are boosted somehow, that have more source and sinks, and improve the quality of the queries. Okay. Okay, this is the part that maybe is the most appealing for you, I hope. So the idea is we take this approach is based on an old work from some colleagues that proposes this idea for Python. And as I mentioned before, the idea is to somehow infer, in base of a lot of examples, the roles of different pieces of code. So the approach somehow is we have many projects. For each project, we are going to extract something that we call data from constraints. You will see that in the next stage from source sinks and sanitizer candidates, not the real one, candidates. From these constraints that I will explain just in 1 minute, we are going to formulate the idea of the specification, the inference of the taint specification as a relaxed linear optimization problem. And from the solution of this problem, we are going to solve it using a solver. And the solution of this problem will give you some specifications with some probability, and we are going to combine the result for each project in a specification for all projects. These are going to be a summary. This is not very relevant for now. So this is the part that is relevant. So remember the small example that I showed you before, when we have some source, some sink, and some sanitizer. So the idea is to use somehow pro-analysis to find triples. What is a triple? A sort candidate, a sink, and a sanitizer. How? By looking at the code. The idea is I have some pattern. If, for instance, if something I don't know reads for instance like if something is really like a field from some object, it's a candidate for a source. It's a rule because we know that in most cases they came from that. If there is something that is known from specification, for instance, something like a password that we know from a previous specification that is a source, it's a source. And then we have using pre-analysis, we look paths. As I mentioned before, we discussed, if we look for paths between source, potential sink, potential sanitizer. We don't know if they are actually source sinks and sanitizers. Okay? The interesting thing is that these candidates are just potential candidates that we somehow identify by using some patterns. Not much. The idea is we are going to have a variable that tells me if something is a sink, a source, or sanitizer. 0 means it's not enough. It's not a sink or it's not a sanitizer, and 1 is we are completely sure. The idea is we are going to have maybe some probability. Maybe we have a 90% certainty that it's a sanitizer for say something. But at the beginning you can think of 0 is not, and 1 is this. It's a sanitizer, a source, or whatever. Something important, is an implementation detail, but it's important to remember that we are going to analyze several projects independently. If you find a project that has the code like this, it's very difficult to find another project that uses the same variable with the same parameter. Take two different codes that you implemented, it's very unlikely that you have the same code. So in order to have more chances to identify common things, we are going to replace this by something like more like a pattern. Okay, this is a call to a function find an update, and the parameter using a parameter 0. If we get rid of this, and this is very likely this function is used for a library, it's going to find that library several times in different projects.
So when you have no information about some statement, then the three numbers are 1/3.
Say it again.
If you have no information, you don't know if it's a
yes.
source or a site,
yes.
then you put 1/3 in each of them, or
technically, we have some rules. For instance, if a function is a candidate of a sanitizer, as he mentioned, a function is a candidate as a sink if there are some conditions. There are some syntactic conditions, but there is something that's important that I will mention later. We have like a previous specification. Remember that it has some specification that is incomplete, it's not good, but you can use that as a starting point. If you have something, for instance, Sergio knows that his function get password is a source. When I can use that, then I know that if there is this source that we are sure that is a source, and there is a path to another function, this function is likely to be a sanitizer, because after using something that is get password, it passes through this function. So this is the idea. The idea is to use some previous information to somehow give more points or more probability to another functions.
But you initialize that with 0.
At the beginning, everything is 0.
Exactly. You initialize with 0, and then
Then I misunderstood, because I understood that 0 was that you are sure that it's not.
Yes. Actually, what you do is
Not is that you're not sure.
yeah,
that
they
it's
should
not.
initialize.
yes. It's not initialization in the sense that you are going to write a linear problem. A linear problem has no initialization. It's between 0 and 1, and it has to find the optimal value. I will go to that in just 1 minute.
I was thinking the interpretation. What means 0? What means
0 means I'm sure that this, for instance,
And then you're sure of something.
if I put this, and I put this element.
I understood your question.
It's as informative having a 0 as 1 is you are sure of something.
Yes. 0 and 1 is when you are certain about something.
The less informative should be 0.5 or something like that.
0.5? Yes.
That's a little bit more.
0.5 is like a code. Okay, there is.
Yeah,
Yes.
exactly. And then if you have 3 options, as an initialization, you take 1/3.
Yes, but
Yeah.
You will know anything.
maybe, but
Can be if I use 1/4 because that will be none of that.
but maybe the result of
It can be none of them, that's right.
yes. So the idea is, let me just advance one slide and maybe it's crystallize a little bit. But the idea is to
But no, there is 0, 0, 0.
For instance, take this X.
No, there isn't.
It can be 0, 0, 0, it can be 1, 1, 1.
There is no
Or 111 actually is, yeah, it's
yeah?
Yes.
right because you don't accept.
It's not a new.
But for instance, take this particular text, find, write, and apply. And then you say, this as a source maybe has 0 because it's not a source. This as a sanitizer maybe has 0.5 because I don't know. And as a sink, I'm sure, because why I'm sure? Because I see that in the specification of Sergio, he already puts this sink. So I can have 3 values, but actually I can have 0, 0, 0, I can have 1, 1, 1. It depends, it's free. The constraint is that is between 0 and 1.
Yes.
But the interpretation is 1 is sure, maybe he was wrong in specification, no? And 0 is not possible, and then in the middle is okay. So the idea of using this approach is to try, you are somehow more coercive, because now when you write that, you are mention this, but another cases that maybe they are not synced. So you lose some precision, but then to try to be coercive enough in order to combine information from many projects. This is just an application detail. Let's continue. Now this is the part that's important. So how we include this constraint, the constraints. So the idea is, suppose that you have previous information from Sergio, and you know that there is something that is a sanitizer, like this public function, I don't know the name, and something that's a sink, and they are connected. So you know that there is a flow from the sanitizer to the sink in the code. So there is a flow, there is a way to go from one to another. And then you find something that is connected to these two. So this element that is connected to the sanitizer, that then is connected to the sink, you don't know what it is, but it's a very good candidate of being a source. Because if you have a source, remember, something that is sensitive, and there is a path through a sanitizer, and you are sure it's a sanitizer, and there is a sink, it's very likely that it was something sensitive that was sanitizer. So, and then this is the idea. So, when you find something like this, you have something like sanitizer, so very candidate, very elements that are candidates, you end up adding an equation like this. I don't know if you can read it because it's a little bit small, but something to say something like this. The value of the sanitizer and the value of the sink has to be less than or equal of the value of these 3 element candidates plus a fixed constant. And let me show you an example that tries to clarify why we do that. Think for a moment that you know that this is a sanitizer, so it has value 1. You know that this is a sink, it has value 1. And then we use this constant, that's something that we use to adjust the model, but in this case it's 1. Very fixed. So in order to comply, even this being 1, in order to comply to this equation, you have to be, at least one of the elements has to be 1. Maybe it has to be, you can have 1, 1, 1, or you can have something that, it has to sum plus more than 1 in order to comply to this equation. So the idea is this equation forces you to somehow higher the number of this element. So the idea is, every time you find something like this, you add this constraint. And you are going to find a lot of this, because you have a lot of paths for program elements to other program elements. So you end up adding a lot of data flow constraints that essentially look like this.
The probability, the interpretation of the...
It's like saying that at least one of the inputs is.
Yes. So the idea is to somehow model your idea in a linear problem, and this has to be more with feasibility. You know, here I just use integers, no? But the idea is that if you have only 0 and 1, it's very likely that the solution of the problem is unfeasible. So the idea is you have to play with this constant and some epsilon, and you replace the integer by real numbers in order to produce you have a relaxed linear problem, not integer, which is much more difficult. And the idea is, once you have these constraints, you repeat this idea also for sinks and sanitizers. For instance, that's something that you are sure that is a source, and you have sanitizer, and you have an element. You have several elements that looks like sinks, you apply the same approach to create more constraints. Yes?
Any constraint, there is any condition on the number of constraints, given the number of
potential sources,
Yes.
potential scenes, and potential sanitizers.
Yes.
There is any constraint in the number, there is any theorem or whatever that tells you how many constraints do you have to add in order to have, to have a solution, the problem has a solution.
Yes, but in the case, in our case, in order to have a solution, we have to play a little bit with the number of constraints, but the problem was more about memory of the solver, not feasibility of the solution. So the feasibility of the solution is if you restrict everything to 0 or 1, it's very unlikely or very likely that the solution is not feasible. But once you work with reals, you can find a solution. But the problem is the scale. If you add a lot of constraints, the solver is going to suffer a lot.
The solution is unique.
No. Okay. No, in general, no. But before talking about that, maybe I can show you how is the model. So now the question is okay. So the idea is, in order to find one solution or one interesting solution, what we are going to do is going to write these systems as a linear problem, adding all the constraints that we already mentioned, these first constraints that I mentioned in the previous slide, adding the constraint that the value has to be between 0 and 1, and also using the information about previous specs. For instance, Sergio knows that some particular node is a source. He will put 1 in this node, in the representation of this node, and 0 in the others, because it's not a sanitizer, it's not a sink. What in that case, you have a lot of constraints. You try to find the one that minimizes several parameters. In particular, we minimize this number of epsilon that we use for the constraints in order to relax. So this is a parameter we use in order to have more possible solution instead of having this fixed. I don't know how to cover that. We use relaxation mechanisms in order to make the problem feasible, and we try to find for each case the minimum value of this epsilon. And yes, this epsilon somehow provide us. I'm not a mathematician, so maybe I say something wrong. But having this relaxation ensures that we have a solution. Maybe the solution is not very good because maybe even if you minimize this, the value of epsilon is a big number. So in order to make everything fit. But you always get a solution. Maybe the solution is very bad in the sense that you get a very low probability for all the elements and a very big value for this epsilon. But you always get a solution. My issue as a computer scientist was more the implementation of this, and it is fixing memory. So this is why I had to, at the beginning I mentioned, I applied this technique for every project in separation, because ideally, the best thing is to have all the projects together and produce one system, but it doesn't scale. So the idea is, once you have this system, you optimize it and you run it, and what you get at the end is value for these variables, no? For each of these variables. So at the end you get something that is a kind of triple saying, okay, I have this variable, a role as a source, as a sink, or a sanitizer, and the probability. For instance, I can say, find by update as a sink has 0.9 probability. This is the result. Okay? So once you have that, what you do is you get these values, you write as a specification, then you run GraphQL, our analyzer from GitHub, and you get actual things. Let me show you a small example. You have this representation as a sink with this probability. Then when you run it with actual projects again, you get the actual pieces of code, the actual statements that are your candidate, not your candidate. Well, the ones that you decide that they are things, because they match this pattern. Okay. So this is essentially the idea of the first stage. What's the problem? Is that sometimes the prediction is a little bit noisy. We get a lot of false positive. What is a false positive? False positive is, for instance, you say that this is a sink and it's actually not. And why this can happen? It can happen because we don't have enough initial specification. We don't know at the beginning how many are actual source and sinks. And the second is the representation. This is maybe very coarse. Maybe you have a representation that says everything that starts with fine is a sink candidate. And maybe you get a lot of things that has nothing to do. And at the end, you get it as a sink. Because at the end, our specification is a pattern. It's not the actual sink. And this generates false positive. This is why we came up with the second phase. And I'm going to be a little bit faster with that. And the second phase, essentially the idea is, once you predict the sinks, how you understand if something is a sink or not. So remember that you maybe have already information about what is an actual sink, a non-sink. So if you look at the actual code and you see how the sink appears in the code, what are the parameters of the function, what is the code that is before, maybe if you take something that you already know and you are sure that it's a sink and compare the use of your candidate sink in the code, they are using the same kind of parameters, they somehow send the same code at the beginning, so maybe this is the same sink, or maybe not, it has nothing to do. So this is the idea. So the approach is to compare the similarity between actual codes. We are not talking more about patterns. We take a piece of code and a piece of code, we see if they are similar. So let me show you an example. Maybe this is your sink candidate, and what you are going to do is, you are going to, at the beginning, look at the statement and how you invoke it, ignore the code that you already have labeled as actual sinks. Or even better, you have alerts that they are insecure. And you compute something using embeddings, and this is not my specialty, I'm going into details. You compute an embedding of this function, and you compute how similar are these embeddings to the actual sink that you predict. And we do something more, which is looking at the context. Okay, let's see, I call this function, but I have all this code before. Now I look at the code that I already know that they are sinks, and I see if they use it in a similar way. For that, I compute an embedding, but now not only for the statement, for all the piece of code, okay? And I look if I found something similar. If I found in my database of known sinks something similar, I say, okay, this sink candidate is actually very likely to be a sink, and I update the scope. So the idea is to take the scores, the original score from the previous approach, the probability, and update it somehow. Maybe you can do an average or whatever you want with these similarity scores. Okay? Once we have that, we have our sinks prefined because we have somehow updated all the scores, and now we can go to the last phase, which is the use of a feedback. What's the feedback? The idea is to use feedback from some expert. Let me show you, I can show you, I don't know if I can do it, let me just give you one. It's here, leave. Because I restart my computer, no, I cannot show you because I restart my computer. But it is, I will show you a page like this, when you can see, these are representations, and it shows you for a representation how many predictions they have. For instance, if you have a representation that has too many predictions, maybe this is garbage. For instance, I don't know, if index of is something that is so common that appears in all the code in different uses. So I say, I don't care about that. And the idea is, they will show you a piece of code like this that are ordered by score, and it's a period, I cannot show you the demo, but the idea is, it will show you like a list of all the predicted sinks ordered by score, and it will let you decide if it's something a sink or not. They say, no, this is actually not a sink. And you can ban it. Ban it is you remove it. But it has something that is very nice, which is you can do something that we call ban similar. We use, again, con similarity, and say, okay, if this is not a sink, I will remove all the things that are similar. So maybe you have a list of 1,000 sink candidates, and you start to remove using this feature, and very quickly you end up with a list of 10. And these are, in general, the more likely to be actual sinks. This is our hypothesis and our idea. So this is the idea. Look, the first one has a score 1, so it's ordered by by the score that we compute. And again, you have the buttons to decide whether or not something is something that you accept or you want to remove.
Just one question.
Yes.
So here, the main sort of assumption is that if the functions are looking similar, then if one of them is the same, then the other one can also be the same. But from what you said before, I understood that whether it is a sync or not is a result of how it is written. So that may be, I mean, two functions can look similar,
Yes.
but one can be.
Yes, this is why, let me see if I understand. Maybe they look similar, but it's not, this is important. Important is how you use it. For instance, this is why when we show the sync, we don't show only the line. You show the context of use. If you see, instead of showing only this statement, we show, okay, this is the sync candidate and the context of use. So you can see a little bit of code. If you are an expert, you say, no, this is not a sync. Or this is clearly a sync. Because actually, in the tool, the idea is, we couldn't finish that, but if maybe you click here and you go to the actual code in the repo, and you see more context if you need to decide. But yes, you're right. The names only is not useful. So what is useful is the combination of the name, the score, and the context. The context that you need.
Another way of asking my question is, how much context you need to classify it as a sync?
Difficult to answer. In our experiments, with this amount of information, the expert of GitHub, for them, that was enough. But they have a lot of previous knowledge. You know, essentially, their work is to look at code and say, okay, I see a rule here. So they are very fast, and very clever, and very trained. But I don't know actually how much in it. It's a very post. So evaluation. I'm not going to detail into this, but if someone is interested, I have the numbers and the experimental setup. But this is a question that we ask for the evaluation. The first one, which is the basic one, is if actually our tool finds new things that are not covered by the handwritten models. So this is a provoke, no? It's actually, we can find new things. When we talk about new things, we talk about true things, because maybe you can produce a lot of information, but it has to be someone that is relevant, okay? The second one is how much effort actually it takes to triage. Triage is what I show the manual, the screen that you put banned or not banned or whatever, and how much effort it takes. How important are the different components? I show you 3 components of the tool. And the last one, which is important, is, okay, you get new things. You can use that to find actual alerts, because a sync is something that you use in a specification, then to execute a security query. So at the end, what you want is to find more security alerts, okay? So briefly, okay, we experiment with these 3 kinds of security queries. We take a relevant number of projects to analyze. Then every particular question has a lot of detail how we do it. I'm not talking about that. If someone is interested, we can discuss later because I have the material. So answering the questions, yes. So our approach to find new things is interesting because we found new things. Some of the things that we reported on GitHub, and they actually added to the specification. They were very happy because they were critical things. Not everything is so cool because we also find a lot of many false positives. So maybe we produce, I don't know, 10 great things, but in a list of 100. Okay, so triage is super important. In the experiment, when we try to do this, we also identify optimal scores for the prediction. So if you run your code, you use a score greater than this, you get rid of something that is very coarse. Remember the representation. How many elements get each representation? It's bigger than 20% of the elements. And code similarity score, very high, 0.9. If you use these parameters, you actually get a list which is very good curated somehow. It still has false positive, but you get rid of a lot of things. Effort. We actually realized that using a good score, the filter I mentioned before, and the coarseness removed a lot of false positive, but still 1/3 of the false positive, which can be a lot, has to be removed through triage. Look it manually and use this one similar. How relevant are the components? The most important one is the first one, because if you think about the code, millions of lines of code. So this one is the one that you take all the code, which is almost infinite, and produce, I know, maybe 10,000 candidates. But 10,000 out of millions is, even if the result is not good, because 10,000 is a lot, it's just orders of magnitude the importance. Then the code similarity at least cut the output of Sheldon in 1/3 at least. So, and of course the triage is the last stage, which helps you to remove the last one. And finally, which for me was very important because it was the goal of my collaboration, we really can predict new security issues. Well, essentially what we did is we took a query, like the old query, for instance, from Sergio, which is not very well maintained. We updated with the information, with the predictions, and run again the query, and we find new security alerts, which is super important. Because even if we have false positive, we can actually find new security bugs, which is relevant. Okay, summarizing, this is what we did. This process we call InspectJS. Essentially, the most important element is the first one, Sheldon, is a data flow analysis of complex JavaScript code that produce sinks using this probabilistic approach, which is finally modeled as a linear optimization problem. We have use of code similarity to improve the quality of the output, and at the end, we have produced a user interface in order to help the actual modelers to decide which are sinks and which are not. And with that, I finish. Good. A little longer than expected, but open to questions.
Questions or comments?
Yes.
More a curiosity, because you mentioned that you were using machine learning, something that you didn't indicate.
Yes.
But what are the tasks that these machine learning techniques perform? What is the type of methodology you're using?
Yes, essentially what we did. Let me just go there. When we talk about this code similarity, so we take somehow something that is pre-trained. We use something that is the name is GraphQL. It's a technology that is already implemented with compute embeddings. It was trained with billions of lines of code of C, C#, Java, and JavaScript. So essentially, this I will say something very brute. Box, given any piece of code, it gives me an embedding which somehow it codifies this piece of code with this embedding, and I compute using this embedding a distance between this one piece of code and another piece of code. And how it is done, I can speculate, but it's not my field.
What is a neural network?
Yes, it's a deep neural network. It's this codebird. It's a transformer. It's something very well known. This is codebird. It's an adaptation of BERT for code, and GraphQL. It's something that tries to instead of using only the code as text, you also use a graph representation to somehow model the flow, because the code is important flow, not only the text.
Because it's what we call dimensionality reduction. So
yes, exactly. Yes.
That maps it into a small dimensional space, just in order to
it's
able to compare things and to make
yes. For me, as an input-output, this is I take something very complex and then it's a low dimension. But I really don't. I tested a lot. I consulted with experts, but I don't know actually how it works. So I can understand the output that it produces, but not how.
normal.
Yeah.
Any other question? I have a small one. When you have automatically produced code, like Copilot or something like this,
Yes.
would it be possible for Copilot just to label the instruction saying this is a sink, this is a source, just there you have? I mean,
I guess yes, but it's based on previous knowledge. So somehow, in some place, it has to know that something is. But yes, having like an initial set of functions, I believe that Copilot is very capable of creating new code and say, okay, this is because somehow the technical is going to be similar.
Yeah.
Yes. Yes. And also the same chat GPT. Yes. Yes.
Maybe it's a stupid question, but how do you obtain the flow of a program? Because I assume that the flow basically means that if you have if statements, then the flow has different branches, but if you're going to run the code in a different set of inputs, how do you obtain it?
This is the question for someone that does for analysis. So there are like two different, practices, paradigms of way of seeing the life from analysis. One point of view is the dynamic analysis, testing. Okay. You know that someone flows from one point to another because you run the code, you see, for instance, when you do testing or something, you say, okay, I see, you can print. I pass through this statement and then print, I pass through. So you run a test and you see it, good. This is a dynamic analysis approach. It depends on execution of the actual code. And if maybe you think about that because you think about the if statement, you cannot guarantee that you pass through all the code because it depends on the input. The static analysis approach is completely the opposite. The idea is you look, so if you are a human, you look at the code very carefully without executing and you imagine all the possible inputs. This is impossible because they are infinite, but you somehow say, okay, this you have like classes of input that does similar things. As you think, suppose you have an if statement that says if x greater than 0. Okay, if I put a 1, it's going to be greater than 0. If I put a 2, it's also, so you have like a whole family of inputs that go through this path. And if you put 0 negative, they are going to go to the else branch. And static analysis tries to mimic that kind of thought, but mathematically, symbolically. This is that Sergio mentioned at the beginning. It tries to perform a semantic analysis in a symbolic fashion.
Okay.
But yes, you had to somehow manage to simulate all the possible execution. How? There are a lot of techniques. One technique is what I mentioned. You have families of inputs. Instead of saying 1, 2, 3, you say, okay, positive numbers, negative numbers, and 0. You have three elements. Instead of and you somehow you have infinite numbers, and now you have 3 kinds of elements: positive, negative, and 0. This is the kind of techniques, the kind of abstraction we apply to come up with a solution without running the code. Of course, what happens if you have several if statements and something is you start to over-approximate because you don't know. It's something, since you don't have the actual input, maybe sometimes you cannot decide if you're going to go through one branch to another branch and say, okay, I'm going to take both. So something that maybe is not reachable because the only way to be reachable is passing through different, for instance, in one if through the then and another if from the else. And this is not possible because you have something x is positive and the other is x is negative and it's not possible. And static analysis will say, I don't know, for me it's possible because I just traverse through that and
Okay.
yes. But good question. Something else?
Okay, that's it.
Thank you very much.